All right, so we're going to look at integration by substitution. So when you get given complex integrals, sometimes it can be hard to get it into a form that you know how to anti-differentiate. So that's what we're going to look at. Basically, you're looking for a situation where you have a function and you've also got the derivative of that function inside the integral. So let me show you what something like that might look like. So if we look at this, 2x multiplied by cos x squared dx, we can see that in the integral we've got an x squared, but we can also see that the derivative of x squared is 2x. And so when you've got that kind of situation, you can use this substitution technique. And algebraically, the substitution technique never really never sit properly with me. I always like to see a picture of a graph of some kind. So that's what we're going to do today as well. But algebraically, we're just making a simple substitution. We're saying, all right, let u equal x squared, in which case du equals 2x dx, if we just rearrange it. So we're differentiating both sides there. So we end up with du equals 2x dx. And then so if you substitute u in now, you're going to get the integral of cos of u du as what you're actually trying to solve. But that, I don't know, to me, it just felt like, I don't know, never felt real. So what we're going to look at is a picture. So the first thing we're going to look at is the graph of 2x cos x squared, which looks like this. And if we actually shade the area between 0 and 2, we get something like that. And I encourage you to go off to GeoGebra or Desmos and sort of sketch it out to see what the function looks like otherwise, but just in this sort of local region, it looks like that. And what we can say is we can just calculate that area using computer. Obviously, we wouldn't know how to do this without making this substitution, but we get a signed area of approximately negative 0.76. But with this substitution, we can see that we're basically going to change the x-axis to be the u-axis, and then that's going to make it x squared along the x-axis. So we're going to change it to be the u-axis. So we're going from sort of xy space to uy space. So we're going to be in the uy space now. And so you see how this makes this change. So that point 1 became 1 squared, which is 1, and the point 2 became 2 squared, which is 4. And so the integral between the same points it stays the same. So you get the area is approximately negative 0.76. as well. So, and that's obviously a much easier and friendlier integral to work with. So we work out the area from 0 to 4 of cos of u, rather than working out the integral from 0 to 2 of that more complex initial function. If you're interested in why that's the case, more so, I'll put a link below to a previous video that I've done explaining it in more detail. But basically, it's a reversal of the chain rule. If you understand the chain rule well, to do integration by substitution is to basically undo the chain rule. So I'll put that link below as well. But if you have any questions or would like some private tutoring, just let me know. Happy to chat, and good luck with all your studies. I'll talk to you soon.